In the last few lectures, we've surveyed the universe at its largest scale, distances of billions of light years. And now I'm going to the opposite extreme. In lecture 33, I want to tell you about the structure of matter at its tiniest scale, a scale much smaller than the atom. And it turns out that atoms are composed of even smaller particles called quarks and leptons. I'll begin by trying to give you some sense of the philosophical basis for the way particle physicists approach their subject. This is very abstract ground we're about to tread, and it might help you to understand why particle physicists ask questions the way they do. Then we'll take a look at the tools of this esoteric branch of physics, their great particle accelerators and daunting mathematical theory. That's how we tackle the subatomic world arm in arm. I'll walk you through the particle zoo and try to make some sense of the confusion of subatomic beasts. Finally, I'll look once more at the Big Bang from the perspective of the unity of all matter and energy and forces in the universe. This is a big challenge, so let's get started. Particle physics, it's a subject of astonishing connections. You know, it often amazes me the way that seemingly unrelated aspects of the material world are interconnected. We've seen these links frequently in the past several lectures. So Isaac Newton, he saw connections in a falling apple and the orbiting moon. And then Hans Ørsted, remember, he found a link between electricity and magnetism. Benjamin Thompson, who is known as Count Rumford, he demonstrated the equivalence of heat and other kinds of energy. Well, it turns out that the same kinds of connections are made when you study the nature of the atom. Exploring the nature of atoms at the smallest scale of the nucleus leads directly to a deep understanding of stars, which are giant nuclear furnaces. And then the study of stars leads back to the understanding of atoms, because stars manufacture all the elements of the periodic table. And here's another surprising connection. Studies of distant galaxies led to insights about the origin of the universe in the Big Bang, as well as the ultimate fate of the universe. But to know that fate, we have to understand the mystery of the missing mass or dark matter, which once again takes us back to matter at the smallest scale of subatomic particles. Well, before entering this subatomic realm, I have to set the stage by considering a philosophical point. How exactly does a particle physicist think about the universe? What guides one's thinking about objects that we can never directly see or touch or measure in any immediate and tangible way? I'd like you to imagine walking through the center of a small New England town, and there are two houses that sit side by side. Now, the first house, it's neat, it's symmetrical. It has clean white paint, perfectly arranged black shutters. Imagine there are carefully manicured rows of bushes, a perfect white picket fence. Now, the other house is similar, but it has a few nagging imperfections. Let's say the white paint is chipped a little bit. One shutter is sort of hanging askew. The bushes are untrimmed. Maybe that white worn fence is missing some of its pickets. You notice those differences, and most people find the neat, symmetrical house more appealing. Well, it turns out that physicists are no different in their search for symmetry in the universe. Most physicists, though I have to admit not all, are convinced that our universe must be tidy, neat, symmetrical. They believe in the mathematical elegance and simplicity of our universe, and they want it to possess order and symmetry, sort of like a neat New England home. It's the quest for this deep symmetry in nature that leads to one of the greatest challenges in physics. That's the search for a theory of everything. That's a set of equations, a single set of equations that describes the properties and behaviors of all the different kinds of matter and forces in the universe. This quest is an example of reductionism. That's the attempt to describe the physical universe in terms of just a few simple basic building blocks. In an extreme, a proponent of this reductionist philosophy might argue that all the natural phenomena are predictable consequences of the behavior of the smallest particles and their interactions. So, according to some chemists, you can understand materials by the behavior and interactions of their atoms and nothing else. Biochemists might argue that you can understand cells by the behavior and interactions of their molecules. And there are behavioral scientists who suspect you can understand people by a study of their genes. Now, other scientists would argue that many collective properties of matter are not predictable a priori from particles. In any complex system, certain unexpected properties may emerge. And we can point to lots of examples of these emergent properties. I mean, think about the interaction of atoms. A few atoms are just particles, but put countless atoms together and you get astonishing emergent phenomena. For example, put enough heavy atoms together and you wind up with a planet like Earth. That's a planet that exhibits weather and geological upheavals. Surely it would be incredibly difficult to predict the properties of planets just from a knowledge of atoms and their interactions. And then think about cellular life. Life emerges from the interactions of various organic molecules, but living cells, they display levels of organization and behavior that would be fiendishly difficult to predict from just the behavior of individual molecules and their interactions. And there are even more puzzling levels of emergence that arise from the interaction of brain cells. As countless trillions of brain cells interact, there emerges a phenomena of consciousness. And it's really difficult to imagine that studies of the behavior of individual brain cells could ever lead to a prediction of self-awareness. So I don't think reductionism is the whole story in science. I'd argue that the emergent behavior exhibited by planets and life and the conscious brain, they're not easily derived from the behavior of atoms or molecules or cells. A lot of progress in devising a theory of everything is made by experimentalists. These are called high-energy physicists or particle physicists. These scientists specialize in accelerating bunches of subatomic particles in big machines. Then they collide these fast-moving objects with other particles at high velocities, and they detect the various fragments as they go flying off in all directions. Now, as these physicists probe smaller and smaller pieces of matter, they need higher and higher energies in their collisions. That's why, as we'll soon see, you need big machines to study the smallest particles. The general term for the experimental devices of these particle physicists are called particle accelerators. The experimentalists work hand in hand with theorists, and the theorists devise all kinds of complex mathematical models of forces and matter. You might think that most scientists would be well versed in aspects of all the sciences, but that's absolutely not true. Not 1 in 1,000 scientists could follow along in most seminars in theoretical particle physics. These theoretical models are, of course, constrained by experiments on particles, but the mathematical models also make predictions which guide the experimentalists in additional experiments, and so the cycle of theory and experiment continues. I've occasionally heard silly debates about which is more important, experiment or theory. In fact, neither could exist long without the other. I have to say, I find it somewhat ironic that the mathematics of theories of everything, though, they attempt to explain everything in the physical world, but they're so abstract, they're so much so that relatively few people in the world actually understand the subject. For one thing, most models end up describing the natural world in many more dimensions than the 4 dimensions of space-time that we experience. You'll occasionally see references to 10 or 24-dimensional universes in the popular press. And believe me, even if the mathematics works out perfectly, no one really understands what it means to talk about a 24-dimensional universe. Let's look for a minute at the hardware of the particle physicist. Particle accelerators are big machines. They employ powerful electromagnetic fields to accelerate a beam of charged particles. Now, these speeding particles collide. They produce showers of fragments, and then massive detectors record the energetic passage of these bits, these fragments. And then intense magnetic fields bend particle paths that reveals their mass, their electric charge. The earliest high-energy physics experiments used the irregular and very unreliable stream of cosmic rays. Those are high-energy particles that stream in from space all the time. The Earth's surface is constantly bombarded by these energetic particles, but you sort of have to wait for them to come along. It's an erratic source of particles. So in the 1930s, Berkeley physicist Ernest O. Lawrence, he invented the first particle accelerator. It's called a cyclotron. Now, cyclotrons used electromagnets to accelerate electrons to near the speed of light. And once the electrons were up to that speed, they were allowed to collide with other particles. And then there's subsequent machines called synchrotrons and linear accelerators. These can be several kilometers in length. Synchrotrons are giant circular rings up to 1 kilometer or more in diameter. And then charged particles like protons are accelerated into a circular path, and they can be held in orbit at relativistic speeds for many hours. By contrast, linear accelerators are, as the name implies, long and straight, sometimes several kilometers in length. Charged particles are accelerated down that long tunnel one time only before they crash into a target. Probably the most famous of the big particle accelerators was the one that never got built. Do you remember the superconducting super collider? That was a mammoth synchrotron accelerator that was begun and then canceled. It was to have been a circular facility 85 kilometers around. Now, at a cost of $12 billion, it wasn't bad science. It was just way, way too expensive. This desire of physicists for larger and larger machines isn't arbitrary. It isn't greedy. It turns out that the only way to observe and study more massive and more ephemeral particles is with larger, more powerful machines. Remember Einstein's equation that relates mass to energy? High energies are needed to make massive particles according to that equation, E equals mc squared. An electron's mass is on the order of 1 million electron volts, or 1 MeV. Now, a proton's mass is approximately 1 billion electron volts. That's just a unit of energy. That's 1 GeV. So you need an energy of at least 1 billion electron volts to study all the attributes of a proton. And it turns out that there are many, many particles that are much more massive out there. Particle accelerators reached tens of GeVs in the 1950s, and then hundreds of GeVs in the 1970s. It reached a tera electron volt in the 1980s. And a machine under construction in Europe will soon achieve 10 teravolts. That's 10 trillion electron volts. Of course, bigger particle accelerators are more expensive. They require more support staff. In fact, it's become routine in the world of particle physics to have hundreds of co-authors on a single short paper. In one recent study on the behavior of quarks, the list of authors was literally longer than the text of the article. Okay, the name of the game in particle physics has been to smash pieces of atoms together and see what fragments are produced. The proton, the neutron, the electron were discovered by the 1930s, as was the neutrino. Then gradually, as particle accelerators became more and more powerful, more so-called elementary particles were discovered. There was at one point in the 1960s when there were literally hundreds of seemingly different particles, each with a set of characteristic properties: mass, electric charge, spin, other sorts of properties. Everyone involved realized that this was a silly situation. You can't have hundreds of fundamental particles. There had to be some underlying order to this. And making sense of these particles was quite similar to the task that confronted Dmitry Mendeleev 100 years earlier. See, Mendeleev was faced with 63 different chemical elements, and he looked for periodic properties. Well, the task facing physicists in the 1960s was just like that. The first step was a search for patterns among the diverse particles. One key step was the recognition that some particles never reside in the atomic nucleus, while other particles always appear to be associated with nuclear processes in one way or another. So here I have to introduce some new and probably unfamiliar names. I'll keep the number of these names to a minimum, but please bear with me. First, we have leptons. Leptons are a class of 6 different particles that don't exist in the nucleus. And we've already met the negatively charged electron and the electrically neutral neutrino. 2 of the other leptons, the tau particle and the mu particle, are charged like the electron, but they're quite a bit more massive. And the remaining 2 leptons are the tau neutrinon and the mu neutrino. Those are particles that are electrically neutral. Strong evidence now exists that neutrinos can transform spontaneously from one kind to another. That's a feature that, by the somewhat obscure rules of particle physics, indicates that neutrinos must have a slight mass, perhaps a millionth of an electron mass. Okay, the other major group of particles besides leptons are the hadrons. Hadrons include all the varied particles that can reside in an atomic nucleus. So that group includes the proton and the neutron, and there are hundreds of other hadrons, some of which are extremely short-lived. They've now been identified. This diversity of hadrons suggested to many physicists that more fundamental particles might exist. This is the same sort of logic that all the elements are composed of different combinations of protons, neutrons, and electrons. So there are lots of different elements, but only 3 subatomic building blocks. Okay, so now we come to yet another group of truly fundamental particles. These are called quarks. They were first proposed in the late 1960s by the American physicist Murray Gell-Mann. Quarks are a curious class of 6 different particles that always combine in groups of 2 or 3 to form all those many different hadrons. Quarks are quite simply weird. They're just not like anything else in this world of particles. For one thing, we can talk about their individual properties, but isolated quarks don't exist. Also, all the quarks have fractional electric charges, either 1/3 or 2/3. The 6 quarks differ from each other in mass and other properties, and they're given fanciful names, such as the down quark and the up quark, the bottom quark and the top quark. So quarks are only found in combinations of 2 or 3 that produce an integral charge. The proton, for example, forms from 2 up quarks, each with a plus 2/3 charge, and 1 down quark with a minus 1/3 charge for a net charge of plus 1. Now, the existence of quarks was demonstrated by scattering electrons off hadrons, and then you saw an occasional deflection. And that experiment was in principle a lot like Rutherford's original experiments, when gold nuclei were observed to deflect alpha particles. Remember, Newton observed that nothing happens without a force, so there must be something massive inside a hadron to deflect the electrons. I want to put quarks in a bit of a perspective in terms of the atom. So starting with this molecule, let's look at the building blocks of matter. Okay, molecules are made of atoms. And then you can talk about atoms, which are made of the electrons circulating around a nucleus. Then look at the nucleus. The nucleus itself is made of protons and neutrons. You then have a proton, which is made of quarks. And we still don't know if quarks are made of even tinier particles. Now, any scientific theory has to lead to testable predictions. The theory of quarks was no exception. It predicted the existence of 6 different quarks, but in the 1980s, only 5 of these particles had been confirmed. This is a case where a larger particle accelerator was essential. In May 1994, the last and most massive of the 6 quarks, the top quark, was discovered exactly as predicted. So the great complexity of fundamental particles has been reduced to the comparative simplicity of 6 leptons and 6 quarks. But we're not quite done. We also have to contend with antimatter. In 1932, a young particle physicist at Caltech by the name of Carl Anderson performed a cosmic ray experiment in which collisions produced streams of particles. A few of these particles had the same mass as an electron, but they spun off in the opposite direction in a magnetic field. Now think about that. Those particles were something like an electron, but that curious behavior, spinning off the wrong way, indicates that they have a positive rather than a negative charge. Anderson called them positive electrons, or positrons. By the way, this behavior of positrons in a magnetic field is an example of what's known as symmetry breaking. In many ways, the electron and positron appear to be identical. That is, until you subject them to that magnetic field. And the magnetic field breaks the symmetry, and you discover that the 2 particles are really different. One of the most amazing aspects of the positron is that when it meets an electron, both particles are completely annihilated to nothing but energy. The positron and the electron are complete opposites. The positron is thus called the antiparticle of the electron. Every particle in the universe has a corresponding antiparticle. Now, positrons aren't just some esoteric sideline of physics. They find a vital medical application in positron emission tomography, more commonly known as the PET scan. That's a medical diagnostic technique in which patients are fed a glucose solution. Glucose is an energy-rich sugar molecule that the body uses for food. And in PET scans, the glucose has been synthesized with an unstable isotope of oxygen, which emits positrons. Now, the glucose is carried in the blood. It's taken up primarily by cells that are doing the most work. Well, here's what happens. Different parts of the brain are used for different kinds of mental activity. So parts of the brain that are actively involved in thinking will light up with positron emissions and thus reveal normal versus abnormal brain activity. So the PET scan helps doctors pinpoint chemical processes in the body while they're happening. Now, according to the current model, all mass in the universe is made up of 6 leptons, 6 quarks, and their 12 antiparticles. One of the great mysteries of particle physics is the asymmetry of matter and antimatter in the universe. Think about this. At the time of the Big Bang, a slight excess of matter over antimatter must have existed. On the one hand, this asymmetry seems disturbing. But on the other hand, without such an asymmetry, we wouldn't be here. Okay, so we know all the different kinds of matter, or at least we think we do, but a theory of everything requires more. At its most basic reductionist level, a complete description of the universe requires knowing all the types of matter and all the forces that cause matter to do interesting things. So we have to catalog forces as well as particles. And it now appears that there are only 4 different fundamental forces in the universe. Remember from Newton's law that a force is the phenomena that enables a mass to accelerate. Every time a mass accelerates, a force has to be involved. And gravity is a universal force that exists between any two masses. The force is relatively weak, but it acts over very long distances of space. And then the electromagnetic force exists between any two electrically charged objects. It acts over long distances and is vastly stronger than gravity, but large objects tend to approach electric neutrality because the balance between positive and negative charges usually occurs. And then we have another force, the strong force, which operates only on the scale of the nucleus. That provides the binding energy for protons and neutrons in every atom. The strong force comes into play in nuclear fusion and fission reactions. This force is strong because it overpowers the electrostatic repulsion of protons when protons get very close together. And then finally, there's the weak force. It also operates only at the nuclear scale, and it's responsible for the energetic release of an electron during beta decay. And now, here comes the really amazing part. According to the modern theory of particles and forces called the Standard Model, all of those 24 different fundamental particles and all of the four forces are at some deep level one and the same. Here we come back to symmetry. Imagine taking all the familiar objects around you and placing them in an immensely hot fire. Now, if hot enough, all the metals and the plastic and the glass would break down to a gaseous mixture of elements. And then they'd become ions, and then a frenzied uniform mixture of protons and electrons. Only by cooling would we be able to freeze out the distinctive materials that make our world so interesting. You see, in the exact same way physicists see the universe today as a place where different particles and forces have frozen out of an earlier uniform and perfectly symmetric time, when all the particles and forces were indistinguishable from each other. One way to imagine this situation is to think ourselves backwards in time to the Big Bang, when all the matter and energy of the universe appeared at a point. So as that hot, compressed universe cools, a dramatic series of freezings, 7 freezings takes place here, shown in this diagram. The earliest freezings involve separation of forces. The first of these, according to calculations, occurred when the universe was only 10 to the minus 43rd seconds old. Gravity splits off from the other forces, and the universal expansion is opposed by gravity for the very first time. At 10 to the minus 35th seconds, the strong force froze out. So there were 3 seemingly different forces at this point. At this stage, physicists calculate that the entire universe was about the size of a grapefruit. Okay, take a look at this. At 10 to the minus 10th seconds, the weak force and the electromagnetic forces separated, so that all 4 forces we experience today had frozen out. Now, subsequent freezings led to the matter that we see today. Prior to 10 to the minus 5th seconds, all particles were quarks and leptons, apparently with slightly more matter than antimatter. At 10 to the minus 5th seconds, quarks combined to form hadrons for the first time. And then, according to calculations, at 3 minutes, the first nuclei of protons and neutrons fused to form deuterium. These nuclei were surrounded by a sea of hot electrons, forming one immense plasma. And then at 500,000 years, the universe had cooled sufficiently that the first atoms formed. That was followed by the gravitational clumping into stars and galaxies and clusters of galaxies. There are a number of excellent books that describe this period in more detail. 2 of my favorites are Steven Weinberg's The First 3 Minutes, and also Jim Treffel's Moment of Creation. Well, this standard model of particle physics, and by extension the universe, seems like a neat little package in one sense, but there are still nagging problems. The mathematical description of the Standard Model requires more than a dozen separate fundamental constants, such as the mass of the electron, the unit of charge, the speed of light, the gravitational constant, and so forth. Each of these constants has to be determined separately. And many physicists feel that this aspect of the Standard Model lacks elegance. Another problem, the force of gravity has not yet been successfully integrated to the Standard Model. The Standard Model doesn't yet fully explain dark matter. Might there be other classes of particles like WIMPs? In fact, some modifications of the Standard Model called supersymmetry double the number of fundamental particles. Finally, consider the implications of finding a theory of everything. What would it mean to discover a single set of equations that describes all types of matter, all forces? Most people would agree with the British astrophysicist Stephen Hawking. He said that the ultimate theory of the universe would, quote, bring an end to a long and glorious chapter in the history of humanity's intellectual struggle to understand the universe. But I ask you, would such a theory be something more? Some scientists claim that such a discovery would mark the end of physics. You see, everything of significance would then be known, according to some physicists, especially the reductionists. Hawking, I think, pushes the hyperbole by calling a successful theory of everything, this is a quote, the ultimate triumph of human reason, he says, for then we would know the mind of God. And then the American physicist Richard Feynman saw a broader hierarchy of ideas. One extreme of this hierarchy, he reasoned, encompassed overarching laws of physics, perhaps someday even a theory of everything. But he said there's another part of the hierarchy. Moving up this hierarchy of ideas, one finds ever more complex concepts. The atom, heat, and then a salt crystal, a thunderstorm, frogs, an ecosystem, and then abstract concepts, history, beauty. Feynman asks, which end is nearer to God, beauty and hope, or the fundamental laws? And he answered, I don't think either end is nearer to God. It may be true that we can't comprehend the mind of God without first understanding unifying laws in nature. But even if we were to devise a theory that explained the workings of all forces and allowed us to predict every possible interaction of matter and energy, we'd still only know the ground rules of the game of the universe. Nothing in that theory could prepare us for the organizing principles of the complexity that surrounds us. In this lecture, I've tried to give you a sense of the world of particle physics and part of physicists. We've seen that this is a world constrained by observations of the smallest particle, 6 quarks, 6 leptons, and their 12 antiparticles. We've also seen that this is a subject of deep mathematical complexity, whose practitioners search for a degree of simplicity and symmetry, and yes, beauty. Whether this pursuit brings us closer to God, however, I leave to your good judgment and your reasoned judgment. In the next lecture, we'll come back to a more comprehensible scale of space, though not necessarily time, as we discuss the origins of our own solar system.